do in this section is we'll talk about functions in Rn. Well, actually, we'll focus on just in R2 because the majority of properties in Rn can be extended to, the majority of properties in R2 can be extended to functions in Rn. More precisely, as usual, we talk about limits of a function and also continuity. Many of you probably is wondering, will those be the same with the function of single variable? Well, it turns out continuity, there is some subtle issue that's actually very different from continuity for a function of single variable. Okay. So here we consider functions of two variables. Two variables. Let's say x and y. Many of you probably will find the beginning of this section will be rather easy. It gets a bit more complicated later. So a function of two variables, that's simple enough. Where the domain of f is obviously a region in R2, maps to some real numbers. Simple example. So this is a rather simple example. I can easily write down the domain for this function of two variables. I'm going to denote this by df. It's all the points x, y that satisfy this. All right, which as we all know is a unit disk. This is x-axis, this is the y-axis, and the vertical axis is the function's value z. Okay, the domain is clearly a unit disk. Okay, it's a unit disk that has radius 1, and the range, that is all the z values. So this is a single real number that is between, well, obviously it's the square root bigger than 0 and also less than 1. Okay, the z value is something between 0 and 1. So that's the domain and range. And the graphs of a function, turns out there are different ways to represent the graph of a two-variable function. So actually we have like 3 different ways. To visualize, okay? To visualize function of two variables. The first one is just sketch the surface. Meaning we're going to sketch the point in, well, R3. The x value, the y value, and z value. Take this guy for example. When x and y is along this boundary here, the z value will be 0. When x and y is 0, the z value will be 1. That's where it achieves the maximum. So the actual graph for this, okay, the actual graph for this, as you can picture, it's like a dome, okay? It's a half of a sphere, okay? It's a half of a sphere. It's a half of a sphere. That's z. Half of a sphere. So that's the first way. The second way to visualize function of two variables is to use the so-called level curves. So what are the level curves? The level curves are the curves in the xy plane. So these are the curves in the xy plane where the z value remains constant there, okay? Remains constant there. the set of all points such that the function's value remains a constant along those curves. Alright, these are the so-called level curves. So with the same example, I can try to visualize this guy by using level curves. So in this case here, we're looking at square root of 1 minus x squared minus y squared equal to some constant c. So by pick different c, I can plot all those curves. For example, if c is 0, you are looking at a unit circle. 1, 1. So along this unit circle here, the level is 0. The level is 0. Somewhere inside there is a smaller circle where the c value or the function's value decreases to 1/2. If you further moving inside at the origin, okay, that's a single point. That's where the c value is 1. So along this circle, that's where the z value is 0 and gets bigger when it moves inside. So that's the second way. The third way that we can visualize this is the so-called contour maps or contour lines, contour curves. So these are the curves, not in the plane, but the curves in space. That is the intersection of the surface and horizontal plane. Okay, that is the intersection of the surface with horizontal plane. So this example that we had is, first of all, you have a horizontal plane on the xy plane, so the intersection will be a big circle. You move the horizontal plane up, you have another intersection of a smaller circle. And the circle gets smaller until somewhere on the top there's a single point. And this is the so-called contour lines, okay, contour lines. So all of this is pretty easy to understand, and this is about the basics for function of two variables, the way that we represent its graph. And now let's talk about the limit. Okay, let's talk about the limit. The following definitions obviously will be important. Let's look at this definition here, okay? Consider a function of two variables. And AB is an accumulation point. And think about why we need this point to be accumulation point of D. We need this to be an accumulation point is so that I can take a sequence, or I can take a sequence that goes to this point, okay? So that there are actually x and y approaches this accumulation point. So here we say, then the limit of f at this accumulation point, the limit of f at this accumulation point is L. Then when x and y is approaching AB, when x, y approaches AB, it's L. If and only if, think about the epsilon delta definition, okay? Given any epsilon, there's a delta. I'm pretty sure that sounds very, very familiar to everybody. So I need a difference between the function's value and its limit to be less than epsilon. Whenever x and y, they have to be in D for sure. Okay, so that's a basic requirement. And the distance between x and y and AB is less than delta. So once again, here we're talking about points in R2. So we use norm here. In general, we're going to use L2 norm. So if I use L2 norm, and this difference here is the same as square root. So this is the usual Euclidean distance, okay? The square root of x minus a squared and plus y minus b squared less than delta, okay, less than delta. Sorry, run out of space there. We should also quickly think about the meaning of this statement back here. So let's think about what does that mean. Recall that this inequality here, okay, less than delta. So this represents all the xy that's kind of close to AB, okay, all the xy that's kind of close to AB represents, well, actually an open ball. Centered at AB, okay? AB is the center here, and the radius is delta, okay, with radius delta. So that's the meaning of this inequality here. Just something we want to quickly notice. So once again, to prove f approaches L, we want to show there's a delta so that this inequality holds whenever this inequality holds, which is identical to this. All right. So obviously the work will be a bit trickier from the limit in R1, but otherwise not too hard to understand. So I show you guys a very basic example here. A very basic example. So here's a two variable function that I'm going to talk about. It's x squared plus y squared. That's simple enough. And I want to calculate the limit at a point AB. Alright, so right now we're only focusing, actually for the rest of the semester, we're only focusing on function of two variables. So the function we're talking about here is x squared plus y squared. Show that this limit always exists at any point, okay? So for any point, so this is obviously a point in, that's right, R2, okay, in R2. The limit itself is pretty easy to see, okay? I can easily identify the limit of this guy will be a squared plus b squared. I just need to prove this, okay? So proof. Let's show the limit of this. It's a squared plus b squared. So what does that mean? Think about that, alright? So that means given any epsilon, need to find the delta. So this is a familiar steps such that if what inequality, the what inequality, right? So if this xy is close to this, the function's value will be close to a squared plus b squared. So back here I need x squared plus y squared minus, subtract this term. I need this difference in the function's value to be arbitrarily small, provided that xy is close to AB. like I said, the way that we measure that distance is to use Euclidean distance. Less than delta. Okay? So obviously this does not feel like easy. Does not feel like easy. You know, how do I pick a delta so that this inequality implies the next? I can barely tell how those two terms are related. So let's work backwards and take a look at this guy. First, I apply triangle inequality. Factor this out. I have x plus a, I have x minus a, which is what we saw here. Y plus b, y minus b. So if you recall, I need to get some estimate on those two terms. I split this into x minus a plus 2a. Triangle inequality again. 2a absolute value, okay? So if I can pick the delta here to be less than 1, if I can pick the delta here to be less than 1, to pick delta to something at least less than 1, then it's pretty trivial. X minus a will be less than 1, okay? So this thing will be at least less or equal to 1 plus 2a absolute value. If I'm going to pick delta to be smaller than 1, okay, so I'm going to pick delta to be at least smaller than 1, then I will have this estimate. Same story for y plus b, okay? I can also make y plus b not to be too big. So you can practice and work this out by yourself. So this will be true if the delta we're going to pick to be less than 1. So now you see this a and b, these are fixed numbers, okay? These are fixed numbers. We're going to call them m, alright? So since a and b are fixed numbers, so I guess I can pick the maximum between those two guys. So we call m to be the larger number between those two terms. Whichever that's big, we'll call this capital M. And in the end, I have x minus a is bounded by, well, m. Y plus b is also bounded by m, because both of them are supposedly less than this number m. So now let's try to see what kind of a choice we're going to choose a delta. So here's the difference between the function's value and its proposed limit. As I said, this is less than the m that we found, x minus a, y minus b. So I want this to be less than epsilon, okay, less than epsilon. Less or equal to, take the m out. I want to make this guy, they are both obviously less than delta, okay, those two terms are both less than delta. But if I can make this less than epsilon over 2m, I can make this less than epsilon over 2m, then the whole sum will be less than epsilon. If we can let delta to be, well, epsilon over 2m, okay? But like I said, delta has to be smaller than 1 to begin with. So I choose it to be smaller than both 1 and epsilon over 2m, okay? Choose it to be smaller than both 1 and epsilon over 2m. Then all the inequalities will work through, okay, will work through. So this is imaginable that to work this directly and work with the inequality using the definition here, it's tricky, okay, it's tricky. I'm not saying it's easy, all right? But this one, if you can follow through all the steps, all the steps just make sense. Let's try to make a few important remark. Okay, a few important remark. These remarks are important. Okay, these remarks will be important. We'll spend about 10 minutes here. Remarks. So here we talk about under what conditions a function has no limit. Has no limit at AB. Number one, if this point, okay, where you're trying to find the limit is, if this point is not even an accumulation point, in other words, it's like isolated point, then you cannot even talk about the limit, because there won't be any sequence or any points approaches AB. You can talk about the function's value at this point, but you cannot talk about the limit. Number two. So let me talk about this one real quick. Let's call this X, let's call this Y. Here's A and B. So X and Y is supposed to approach AB, right? So there are different roots. So for example, I can say I let Y approaches B first. So this is the B value here. Okay, that's the A value for X. I can let Y approaches B first, and then let X approaches A. Or I can also let X approaches A first, and then take Y goes to B. So there are two different paths to get to AB. Obviously, in general, there are infinite many different ways that a point can approach AB. Okay, there are many different paths, but this is just one of them. So this result says, if you take this two-variable function and let Y approaches B first, you're going to find the limit, but X will stay behind. You take this guy and try to let X goes to A. So here you're letting Y goes to B first and then let X approaches A. If this one is different, is a different number than from this path, the other path, which means you let X goes to A first. All right, you actually get a function that has Y in there, and then you let Y goes to B. So if the limit turns out to be different, along different paths, then you can't say this guy have limit, but because supposedly f of xy needs to approach a fixed number no matter how x and y approaches AB. No matter how xy approaches AB. So that's an important result. So a more general statement would be the following. Okay, so this is the more general statement for this guy. If there are two different sequences that one of them we call xn. So xn here does not refer to the x coordinate, it refers to the point on the xy plane. So I can take this sequence to be, say, xn. And another sequence that we call, yn. Once again, y sub n bar does not refer to the y value. Rather that refers to a different sequence here. So I call this sequence yn. If there are two different sequences that both goes to AB, that both converges to AB. You're trying to take the limit, right? You're trying to find out the limit of AB. But if there are two different sequences converges to AB, but the limit of the y values at those points, so this is actually a pair of numbers that you're going to plug in F. But the limit along this path is not the same as the limit of the y value, the z value along the different path, which is denoted by y sub n. If there are two different limits, then we can also say f of xy has no limit at ab. Okay, so that's another important result. So put it simply, if you can find out two different sequences or two different paths that goes to AB, but the function's value does not approach to the same number, then that would imply this guy has no limit. So once again, a diagram for this look like this. Here's x-axis or y-axis. This is supposed to be where you're trying to figure out the limit as xy approaches AB. Like I said, there are so many different paths x and y can approaches AB. There are so many different paths xy approaches AB. But if you can find two different paths, so one of them is called xn, and the other path is what we call y sub n. If you can find two different paths, but the limit of the function's value, those two different paths approach different limits, approach different numbers, then that actually implies the limit at AB does not exist. Okay, the limit at AB does not exist. All right. So I will show you an important example, and I'll use this to wrap up the first half of this section here. So this is a rather important example, okay? Let's look at this guy here. X squared y on x to the fourth plus y squared. We're trying to figure out what happened when xy approaches the origin. So you can picture this. What's going to happen when x and y both turns out to be very small? Kind of hard to picture this, right? Unlike single variable functions, sometimes you can easily figure out the limit, but this is kind of hard to picture. But here I'm asking you, hey, can you show this one does not exist? And here's how I show this. Solution. I take this function. Let's try to pick x and y both approaches 0, 0 along a certain path. You know, when it says along some path, means x and y satisfy some kind of equation. So here, let's say let y to be x squared. So y is always x squared. So along this path. You see this curve right here? When x goes to 0, y is also going to 0. But along this path, that means y is always x squared. So I'm going to replace y with, well, x squared. I'm going to replace y with x squared. Squared again, I get x to the fourth. Okay, so y is always x squared. So now I can only just take x goes to 0, because x goes to 0 automatically implies y also goes to 0. Because along this path, you know, y equal to x squared, right? But you might notice this guy is actually a constant. It's 2 over 2, okay? 2 over 2. This is always a constant along this path. So this function's value approaches 1 along this path. Let's try a different path. Let's try a different path where both of them approaches 0, 0. And this time around, I'm going to say xy approaches 0, 0 along, say, a straight line. Along the straight line where y is given by mx, I can just take x goes to 0 and plug in y equal to mx. Y equal to mx, so you have m squared and x squared down here. And this becomes a single variable limit. You're going to divide the top and the bottom by x cubed, okay? You got a 2m on the top. This is the x. Divide this by x cubed, you get m squared over x. So what is the limit of this when x goes to 0? Fixed number on the top goes to 0. Okay, that's okay, but this term goes to infinity. This term goes to infinity. So the limit turns out to be 0. So here we found two different paths, two different paths where the limit is different. The limits are different. So what's the conclusion? Okay, the conclusion will be, this limit does not exist. Thus, limit does not exist. Okay, limit does not exist. All right, and that's a rather important example. So on the next part, we'll go ahead and talk a little bit more on the limit. Notice we have not talked about continuity yet. Just finding the limit. When do you think the limit exists, and how do you show the limit does not exist? All right, to be continued.